everyone for joining our earlier Monday Zoominar today. We're very happy to have Uri Kol from NYU telling us about a new topological symmetry of asymptotically flat spacetimes. And as usual, we will not be taking the seminar speaker to a dinner at this occasion, but hopefully at some point in the near future, when everything is better, Uri will come back down and we'll show you a good time. All right, take it away, Uri.
Thank you very much, Nima. Thank you everyone for coming, and thank you for the opportunity to speak here. Today I want to tell you about a new structure that we found and explored of asymptotically flat spacetime. And this is based on works with Massimo Porratti and with Yutin Wang and Donald O'Connell. Okay, so as you all know, there are many open problems that are related to the infrared structure of gravity. Here I listed the most famous ones: the black hole information paradox, the dark matter, and dark energy. And there are more problems. All of these problems provide us with a good motivation to study the long distance or the asymptotic properties of spacetime. In this talk, I will not address the problem listed here, but I will address some other problems that appear in the literature, and will explain how we solve them. Furthermore, I will focus on spacetimes that are asymptotically flat, but similar analysis can be done in de Sitter and anti-de Sitter. And I will try to make stops every once in a while to take some questions. Let me start with a very brief review of the structure of Minkowski spacetime, mostly just to set up the notations that I will be using. So in retarded null coordinates that I will use, U, R, Z, and Z bar, the Minkowski spacetime can be written in the following form. Here, the null coordinate U is the standard null coordinate equal to T minus R. R is the standard radial coordinate, and I will be using two complex coordinates on the sphere, Z and Z bar, that are related to the angles theta and phi in a standard way, in the following way. In terms of these coordinates, the Minkowski metric can be written in the following, in this form, where here gamma ZZ bar is the metric on the round sphere, on the unit S2, and it is given by this expression over here. And similarly, one can also define advanced null coordinates, but yeah, I will avoid writing it explicitly. So now the Penrose diagram of Minkowski spacetime looks like that. There are two null boundaries, future null infinity and past null infinity. They are commonly called in the literature scri plus and scri minus. At future null infinity, the boundary of scri plus is described by or parameterized by the coordinate U that goes from minus infinity to infinity. In the following, I will define some charges, gravitational charges. And in gravity, the only way to describe charges is on very large spheres at spatial infinity. And therefore, the charges will be defined at this point at spatial infinity that can be approached from scri plus by taking the limit U goes to minus infinity. So far, this is very standard. And this is the Penrose diagram of pure Minkowski spacetime. What I will do next is to consider general metrics, general spacetimes in the bulk that approach Minkowski, near the null boundary. So in the bulk, I will be agnostic about the form of the metric and the matter distribution In the bulk, I will only assume that it approaches Minkowski around near the null boundary. Any questions about this? Okay, so this class of metrics can be expanded systematically around future null infinity in the following way. Of course, one can use different system of coordinates. I will use the standard Bondi coordinates, in terms of which the expansion takes the following form. So in this equation here, we see the leading term is the Minkowski metric, and then there are sub-leading corrections. The leading correction is written here in the second line, where the different coefficients are called the Bondi mass, MB, and the radiative data, CZZ and CZ bar, Z bar. UZ and UZ bar are they are functions of the radiative data. They depend on the radiative data, so they are not independent coefficients. And all of these coefficients are function of U, Z, and Z bar. And very soon, I will explain why I chose to use these complex coordinates on the sphere. It will prove to be very useful for the applications that I will be using. The dots here represent sub-leading corrections that I will not be discussing today. And finally, one can also define what is known in the literature as the Bondi news, which is the derivative of the radiative data with respect to U, and is non-vanishing in the presence of gravitational radiation. A similar expansion can also be made around scribe minus, almost identical, except for a few small details. But I will not show it in detail because it's very similar. I will focus on the structure around scribe plus. So this is what I will call the Bondi metric, and I'll be using this. Any questions? Okay, this is all very standard. The last thing that I want to review here is the BMS group, which is the group of isometries of the Bondi metric. It is composed of Lorentz transformations and supertranslations that I will discuss in detail. At this point, I want to review and mention a work from 2014 by this group of people, Elisov, Mitra, and Strominger, who argued that in addition to writing down the Bondi metric, one has to impose the following boundary conditions. So these are boundary conditions that relate the CZZ and CZ bar Z bar components of the metric at spatial infinity. So it's very important that these are boundary conditions at spatial infinity. Their argument is based on the consistency of the BMS algebra and the action of the generators, the BMS generators, on the phase space. But the physics is very familiar for us. This boundary condition is nothing but a constraint on the two polarization modes of the graviton zero energy mode, since it's a constraint on the metric components at very large distances, at spatial infinity. So what this constraint is doing, it relates the two polarization modes of the boundary graviton at very low energy. And this is something we are familiar with from field theory. In QED, for example, we know that the two polarization modes of the photon are at zero energy are indistinguishable, and therefore we need to put some constraints that relate them and tell us that they are not independent degrees of freedom. And this is precisely what this boundary condition is doing in the setup of gravity and asymptotically flat spacetimes. So it's not a big surprise. And then one can go ahead, or this group of people, they went ahead and also defined, using these boundary conditions, the solution for the radiative data at spatial infinity, and it is given in terms of a scalar function C, which is real in their work, and it's called the boundary graviton. So we have a boundary condition at spatial infinity, at u goes to minus infinity, and it is defined using a scalar function that is called the boundary graviton. So to give a little bit more details, to solve the gravitational problem here, one has to provide some boundary conditions at spatial infinity here, and then can use the equations of motion to evolve and solve for the metric along the entire null boundary. Okay, so that's the idea in the paper. And yes. Any questions about this? So at this point, I will end the review part of the talk. This is all review of work that appeared in the past. And if there are no more questions, I will give maybe 10 more seconds to take questions. If there are more questions, I will introduce some new results. And I will start with our suggestion for a generalized class of boundary conditions. It is given by the following expression. Here in this expression, the first term, whose coefficient is alpha, is identical to the boundary conditions that I discussed previously. It comes with a coefficient alpha. But in addition, we now have another term that is, in a sense, the orthogonal combination. The difference here is the plus sign. And it comes with a different coefficient beta. Now, the claim is that this generalized boundary condition solves the same problem that Lisov, Mitra, and Strominger addressed in a similar way. It solves the same problem of the consistency of the BMS algebra and its action on the phase space in a similar way. And again, instead of showing the technical details, I will allude to the physical mechanism. And one can say that this boundary condition is doing precisely the same thing. It puts a constraint, or it relates the two polarization modes of the graviton at zero momentum, because it is all evaluated at spatial infinity. So the physics is very similar. It is a different constraint between the two polarization modes, but nevertheless, it is a constraint on these two modes, and therefore it solves the problem of counting correctly the number of degrees of freedom at zero energy. So this is the idea. And it provides a class of boundary conditions because it depends on it's a one parameter family of solutions. There are two parameters alpha and beta, but this class of boundary conditions really depend on the ratio alpha to beta. Yeah, so it's a one parameter class of boundary conditions that we suggest as a generalization of the previous boundary conditions.
Excuse me, Uri.
Yes.
Are you considering this an enlargement of the phase space, or are you, for each value of this parameter, you have a different phase space?
Exactly. So that's what I will discuss now. It will show that we enlarge the phase space. The coefficients alpha and beta are arbitrary but fixed. So the physics of, so we have to fix them. We can choose arbitrarily this alpha and beta, but every choice will correspond to a different physical scenario or different physical situation that I will explain now. So I believe that Tom Banks was asking that question. So precisely, as you said, the solution to this new boundary condition is given by a similar form using a scalar function, but now the scalar function is a complex function on the complex plane, and therefore it introduces a new degree of freedom, which is the imaginary part of the boundary graviton. So this is indeed the new degree of freedom that this new class of boundary conditions introduces. Yes.
Hi, Uri. Can I ask a question?
Yes.
I'm a bit confused about the counting. So CZZ without any constraint
Yes.
already has 2 degrees of freedom in it.
Yes.
One CZZ and CZ bar Z bar.
Right.
And now you have you're writing everything in terms of a function C, and which is a complex function. So that also has 2 degrees of freedom in it.
Yes, but this is evaluated only at spatial infinity, right?
Yeah, but even CZZ at spatial infinity without any constraints has like is a complex function, has 2 degrees of freedom, CZZ and CZ bar Z bar at spatial
Yes.
infinity.
Yes.
And your function C is also a complex function which has 2 degrees of freedom.
Yes.
I'm trying to understand how this constraint is helping us. Is this reducing the degrees of freedom, or is it giving us some relationship between those?
It enlarges the degrees of freedom, the boundary degree of freedoms, the soft degree of freedoms. It introduces a new degree of freedom, a new soft degree of freedom. I will discuss it in more detail, which is the imaginary part of the boundary graviton.
But isn't it true that if I just substitute this solution that you have here into your constraint equation?
Yes.
You'll just get imaginary part of C?
No, what you will get is something, roughly speaking, something like that. I alpha imaginary of C, roughly speaking, maybe with some differential operators acting on this.
Yes.
Plus beta real of C.
Yes.
And the boundary condition that you discussed in your paper is when beta equal to 0, and therefore the boundary conditions that you set is basically setting the imaginary part of C to 0.
Okay, I understand. So imaginary part of C is not an independent degree of freedom. It's related to the real part.
It is related once you impose some boundary conditions, yes. But you are free. The coefficients alpha and beta are arbitrary. You are free to choose them, and you are right that once you choose them, they are not independent anymore.
Okay, of course. Okay.
Are alpha and beta constant on the celestial sphere?
Alpha and beta are, I will take them to be constant, but more generally, they can also be functions of the angles. Yes. So in the rest of the talk, I will not use this description using alpha and beta. I will just explore the consequences of the new degree of freedom, the imaginary part of C. Now, I'm using complex coordinates on the sphere, but at the end of the day, the metric is, of course, always real. This is only a description in terms of complex coordinates that will be very useful for this for these applications. Okay, so we have a new boundary degree of freedom, the imaginary part of the boundary graviton. And now I want to start explaining the physics of this. So first of all, the boundary graviton is acting to the boundary photon in QED. And from this analogy, we can already understand the meaning of this new degree of freedom. The boundary photon in QED has two degrees of freedom, 2 components, the electric and magnetic components. And with this analogy, we can now understand the new degree of freedom. So I will use the parity or the transformation law of these 2 components under the antipodal map to understand the physics. The antipodal map up to rotations on the sphere takes the form of exchanging Z and Z bar. And under this transformation, the 2 components, real of C and imaginary of C, transform as even and odd functions under the antipodal map. This can be roughly seen from the boundary conditions, right? We see that the boundary condition, the term that basically controls the imaginary part here is is odd under the replacement of C and Z bar, and therefore the imaginary part of C will be odd. And similarly, the term that controls the real part of C is an even combination, and therefore the real part of C will be even. And based on these parity properties, we can now draw an analogy with electromagnetism. The analogy goes as follows. The real part of C is analogous to the electric part of the boundary graviton, and the imaginary part of C is analogous to the magnetic part of the boundary graviton. And therefore, it gives rise to a field component that has magnetic properties. Yes. So as we discussed a couple of minutes ago, indeed, for beta equal to 0, we'll reproduce the previous boundary conditions that I will now call electric. More generally, for non-zero alpha and beta, we will have the ionic boundary conditions because they give rise to both electric and magnetic components. So this is the main point, and these new boundary conditions, the ionic boundary conditions, will give rise to many more results that I'm going to present in the following. Before we go on, I will stop to see if there are any questions.
Hi, I have one more question. So,
yes.
The constraint that we had imposed previously, I mean, there was a covariantness to it. It was coming from roughly the imaginary part of the Weil tensor, of some certain component of the Weil tensor. Should I understand this? How should I understand this contribution? Because this is the real part of the Weil tensor contains also the Bondi mass.
Yes. So in 2 more slides, I will discuss the conjugate charges, and then I will address this point. Okay. Okay. So, but before introducing the charges, so as Prahar said, as he alluded for, each one of these field components is conjugate to a conserved charge, and I will discuss this in a minute. But before doing that, I want to explain the dynamics or the physics of the magnetic mode. In order to do that, let me review the solution for the electric mode, and then we'll see the solution for the magnetic mode. So these are solutions to the Einstein equations. The solution to the electric mode, which I write here as the real part of CZZ, with some differential operator acting on it. Someone open his mic. Okay. So now the solution for the electric mode is given by this expression. There are 3 terms here. The first term is the boundary condition. It depends only on the real part of the boundary graviton. This is the electric 0 mode. So this is simply the boundary condition that we set at u equal -infinity, and then using the equations of motion, we develop along with the entire null boundary. Then we have a term that is proportional to the difference between the Bondi mass at u and at u equals to -infinity. And finally, we have a term that is proportional to the UU component of the stress tensor integrated over the null boundary from -infinity to u. And I will call this last term an integrated effect. This is the integrated effect, and it means that a localized distribution of matter can excite the 0 mode. By localized distribution of matter, I mean a T mu nu that is different than 0 at some finite interval. If the stress tensor extends all the way to -infinity, we have an extended infinite source. But the localized source takes this form. And we see that the electric mode can be excited using a local source simply because it's an integrated effect. effect, and that also goes sometimes under the name of the memory effect. So this is standard. And now the solution to the magnetic mode can also be inferred from the Einstein equations. The first term here is, again, the boundary condition, similar to the solution for the electric mode, except that now the boundary condition is given by the imaginary part of the boundary graviton. And then we have a term proportional to the stress tensor, integrated over the sphere with some coefficient here that depends on the Green's function of the problem. That is not very important right now, the exact form of the Green's function. The important thing is that we have an integration over the sphere, but not over U. And this is why I call this effect an instantaneous effect. Okay, because it's not integrated over the null coordinate. And the meaning of this is very important. It means that a local stress tensor cannot excite the magnetic mode. This is an important conclusion that distinguishes the magnetic mode from the electric mode. So the physics of these two modes is very different. There is no memory effect for the magnetic mode, and we cannot excite the zero mode with a local stress tensor. Any questions?
Well, the fact that the expression for the imaginary part is local could make you concerned that when you go to the past of null infinity, it would actually vanish.
This term will vanish.
Okay.
Right, this term will vanish unless we have a non-local source. So in this talk, I will consider only local sources. In fact, I will also mention some non-local sources, but local sources cannot excite the zero mode. So if we don't have a magnetic zero mode, no local stress tensor will be able to generate one. And if we start with some magnetic zero mode, no local source will be able to change it. That's the main point.
Here you're referring to locality on the surface, right? On the celestial sphere?
No, I refer to locality on the null boundary U. I mean locality, locality in the sense that I consider localized sources that do not extend to spatial infinity.
In other words, ordinary particles and radiation.
Yeah, exactly. For an example for a non-local source will be a cosmic string that I will discuss. Yes, yeah. So in a sense, in a sense, it's a locality on the sphere in the sense that a local source will not have singularities on the celestial sphere. So in this sense, yes, a local source will not have singularities on the celestial sphere, and then we can also consider, for example, strings, cosmic strings that will punch the celestial sphere at some isolated points, and I will discuss it. Okay, so now, as Brown mentioned, each one of the field components is conjugate to a conserved charge in a similar way to electrodynamics. The electric component is conjugate to the standard supertranslation charge. It is given by an integral on the sphere over the body mass. And using the equations of motion, this can be inverted into a three-dimensional integral on the entire null boundary. When doing that, we get the following expression that can be divided into two terms. The first term here receives contributions from soft graviton modes only, from zero energy modes only, and therefore it goes by the name of the soft term. And then there is another term proportional to the stress tensor that goes under the name of R term. Now, in addition to the the electric charge, which is super translation, we will have a new charge conjugate to the magnetic component. And we name this charge dual super translation in reference to electric magnetic duality. This charge takes the following form, and there are different ways to derive and understand it. Let me allude to the simplest way to understand it. This charge looks very much like the magnetic counterpart of the soft super translation term. We see that it's very similar to the soft super translation term, except that instead of a plus here, we have a minus, and there is an additional I here to make the charge real. So using this analogy, we can understand the form of this charge. There is no R term, precisely because of the reason that I explained in the previous slides, since there is no local R charge density, so we cannot write local R charge density. There is only a soft contribution, and therefore it is also conserved identically. And we can also understand it using an old method by Newman and Penrose. Today it goes by the name of Newman-Penrose formalism. Newman and Penrose studied the asymptotic properties of spacetime and defined conserved charges. In particular, one of the charges is defined by a scalar which is called psi2, like I think this is what Prahr alluded to. I don't want to get into too much details about the Newman-Penrose, but for people that are interested, I can say more about this after the talk. Now, this Newman-Penrose charge is a complex charge, and it roughly goes like, or its real part is the super translation charge, and it has an imaginary piece, which is precisely what I call the dual super translation. So this charge can also be understood as the imaginary part of the Newman-Penrose charge. So I hope that it answers the question of Prahr.
Yes, it does. Thank you.
Yes. Okay, any more questions?
Reasoning by analogy, I would expect the Bondi mass in the top formula to somehow be related to NUT parameter in the bottom formula. Is the NUT parameter in this?
Right. So I'm getting to this. Yeah, I'm getting to this. Yes. Okay. So now I want to describe few properties of the dual super translation charge and the magnetic mode. I will take a few minutes to describe the properties, and then I will present some applications. So the first property that I want to discuss is the action on the phase space. The action on the phase space. Let's start by reviewing the action of super translations. It is given in by these formulas here. The action on the bonding news, the radiative data, and the boundary degree of freedom. These two terms that are proportional to the U derivatives are the hard parts of the charge. And in addition, we have an homogeneous term. This homogeneous term gives rise to the transformation law of the boundary degree of freedom. And this is precisely the contribution of the word large, here. So these are called large diffeomorphisms. And now we can also look at the action of dual super translations on the phase space. And it looks very much like the imaginary counterpart of the homogeneous terms in the super translation transformation laws. However, there are no explicit U derivatives here. And this is exactly because of the fact that there are no local hard charge densities. And the conclusion from this is that this transformation does not correspond to any diffeomorphism. And one can show, we show in our paper rigorously, that there is no diffeomorphism that corresponds to this transformation. And again, this is reasonable given what I already told you. Since this mode is not associated with any local stress tensor, we cannot associate it with any kind of diffeomorphism. And this is an important conclusion. In particular, I want to highlight that the bond in use is invariant under the action of dual supertranslations. And since the bond in use is considered as the physical characterization of gravitational radiation, it means, and the fact that it's invariant means that we have here something different, not a diffeomorphism. And I would like to suggest that it describes some kind of redundancy. And I will present now further evidence that it describes some type of redundancy. So let me now discuss the conservation of this charge. Before doing that, I want to review the case for standard supertranslation so that we have a point of reference. The conservation of standard supertranslations implies the following word identity or soft theorem that was also understood in the same paper that I mentioned of Braar and Strominger and Lissov. They understood that the soft theorem the soft theorem of Weinberg can be understood as a word identity of soft supertranslations. It relates different S-matrix elements with different insertions of soft supertranslations to each other, as can be seen here. And it is derived from the conservation equation simply by substituting the composition of T into soft and hard pieces. So the right-hand side in this equation is the contribution of the hard terms, and it provides a relation between the two sides. Now, on the other end, we have the conservation law of dual supertranslations written here in this big box. But as opposed to the supertranslation case, in this case, it does not apply the existence of any soft theorems or word identities, simply because it does not relate S-matrix elements with different insertions of dual supertranslation soft modes. As we can see, the conservation law of dual supertranslations directly implies that their action on S-matrix elements is trivial. And therefore, it defines a super selection rule that says that asymptotic states can be classified into distinct super selection sectors according to the super selection charge. And the super selection rule tells us that states from different super selection sectors cannot transform into each other. So instead of having a soft theorem or a word identity that hints at the possibility of spontaneous symmetry breaking, here we have instead a super selection structure or super selection rule. And it implies that dual supertranslations factorize the Hilbert space of asymptotic states into distinct super selection sectors. So this is also a very important result, and therefore I will give you a few seconds to start it and see if there are any questions. Sorry.
Does a given sector correspond to a particular boundary condition?
Yes.
The ones you were.
Yeah. It is defined by the value of the imaginary part of C. So we have to supply, we have to give the values of both real and imaginary parts of C at spatial infinity, at u goes to minus infinity, and that provides us with some boundary conditions that we can later evolve using the Einstein equations.
It would be very helpful if you would tell us a little bit more about what kind of physical situations are in the new superselection sectors.
Yes, yes. So I want to describe, I believe, one more property, and then I will show an example, an explicit example.
Sorry, just one question. So you mentioned that I'm a bit confused. You're fixing alpha and beta, right? Before you start all of this process?
Yes.
You choose your favorite choice of alpha and beta.
Yes.
Once you do that, your real part and imaginary part are not independent. You can't choose them independently.
Right.
Because they satisfy the constraint.
Yeah, but I can choose alpha and beta. So yes. But you're right that once I choose alpha and beta, the two are related.
So your super selection sectors are defined by values of alpha and beta, or values of because the real part of C gives us the soft theorem, the soft theorem we have written in the first line.
Yes.
So for a given choice of alpha and beta, if my real part is fixed by the soft theorem, so is the imaginary part.
Yes.
So you're saying you have different super selection sectors given by the values of alpha and beta, or the ratio?
Given by the value, essentially the value of the imaginary part of C.
Imaginary part. Okay, that's probably.
Okay, let's continue. I'm running a little slow. Let me, I will go over this slide very quickly because it's not essential. We also showed that the geodesic equation is invariant under dual super translations. So basically, I want to claim that dual super translation describes some type of redundancy. We have to ask how do geodesics behave under its action. And basically, we have here the geodesic equation takes a form that is, in this approximation, in the post-Minkowski approximation, it takes a form that is very similar to the Lorentz force in electrodynamics. There is an electric and magnetic forces that comes with different coefficients that depend on the Lorentz factor gamma. And these electric and magnetic forces are defined as, in the same way as in electrodynamics, using two potentials that are defined here at the beginning of the slide. And the bottom line, yeah, I'm running out of time, so I don't want to go into details here. The bottom line is that geodesics are invariant under dual super translations, as opposed to diffeomorphisms, as opposed to super translations, under which geodesics transform covariantly. But here instead they are invariant, not just covariant. This is less important. All of these results provide evidence that suggests that dual super translation describes some kind of a redundancy, maybe even something that looks like a gauge redundancy, but I don't want to use the word gauge. I will just say that it's a redundancy, at least in the sense that the dual super translation mode cannot be observed by local measurements. One more important property before I show an example is the global part of the charge, which is the part of the charge with f equal to 1. When we set f equal to 1, the dual super translation charge is an integral on the sphere over a total derivative, and therefore it vanishes unless the metric is deformed. In which case, it will it will take the form of a contour integral around the deformation. And this property implies that the global part of the dual super translation charge is invariant under any metric deformation that is globally well-defined, that is not singular. And this implies that the global part of dual super translation is a topological invariant on the space of asymptotic metrics. Or in other words, it classifies the space of asymptotic metrics into distinct topological sectors. So that's a very important and interesting property of the global charge. And what I want to do next is to show an example. Okay, so this is the picture that I want to advocate for. which is that this gravitational-magnetic charge, the dual supertranslation charge, classifies the space of asymptotic metrics into distinct topological sectors in the same way that the magnetic charge in field theory classifies the space of gauge fields into distinct topological sectors. And now I will show an example that shows the connection or the link between the dual supertranslation charge, the topology of spacetime, and the magnetic mode. This example is the Taub-NUT metric, as I believe Robert already mentioned. It is given by the following metric, where the RAP function h of r depends on the mass and the NUT parameter L. There are two horizons in this metric, R plus and R minus, that separate the Taub region from the NUT region. And this metric has three important properties that I want to highlight now. Of course, it was extensively studied in the literature, but I will focus on the following three properties. The first one is well known in the literature, and this is the fact that the Taub-NUT geometry exhibits an infinite string singularity along the z direction, along the direction theta equal to 0 and pi. And this is regarded as the equivalent of the Dirac string in electrodynamics. It implies that the topology of this space is non-trivial.
There's a bit of a problem with that. If you want the string to be unobservable, like the Dirac string, then you have to take t to be a periodic variable.
Yeah, I'm getting to this, exactly. I do not claim that it's not observable like the Dirac string. I do not claim that. And I will exactly discuss the point that you mentioned. But for the moment, you can consider the string to be a physical object. Then the next thing that I want to address is the dual supertranslation charge of the Taub-NUT metric. And it turns out that it is proportional to the NUT charge. As we can see, for example, the global part of the charge is simply equal to the NUT charge over Newton's constant. So we can think about the new dual charges as some generalizations of the NUT parameter. And finally, this metric, the Taub-NUT metric, can be written in the Bondi form everywhere except the location of the string. So the location of the string, the metric is singular, but everywhere else we can bring, it turns out, and we show that explicitly, that the metric can be brought to the Bondi form with the Bondi mass equal to the mass aspect and with an imaginary boundary graviton given by this expression. So this example shows explicitly the connection between the non-trivial topology, the non-trivial dual supertranslation charge, and the magnetic mode. Or in other words, if you like, I can say that the dual supertranslation charge will vanish if the topology is trivial. And as we saw in the previous slide, or at least the global charge will vanish.
Don't we expect the topology to be trivial due to the fact that the time is non-compact?
So I'm getting to this point precisely. I'm getting to this. Before I get to, this is called the Meissner construction. Before I explain the Meissner construction, I want to explain one more point. We can also describe semi-infinite strings in a similar way with a metric that is defined by an imaginary boundary graviton that takes the following expression, which are slightly different than the expression that I showed for the infinite string. And now I would like to ask the question, can we construct a monopole solution with non-zero dual charge and without any string singularities? This is our construction, and after I describe it, I will also mention and explain the relation to Meissner construction. So to construct a monopole solution, I will use the redundancy described by dual supertranslations. And I will define the metric using the Bondi form here. For the moment, I will take the mass to be 0, and soon I will generalize it. And CZZ to be a function of the boundary graviton, where now the boundary graviton is defined on two different patches, different but overlapping patches of spacetime. On the node patch, I will take the boundary graviton to be equal to Cn, that, as I explained in the previous slide, describe a string pointing in the negative direction. And in the south patch, I will take the metric to describe a semi-infinite string that points in the positive direction. In such a way, the metric is perfectly regular everywhere, because in each one of the patches, the metric is regular. Now, this construction is analogous to the Wu-Yang monopole in QED, but we still haven't finished, because we need to show that the solution is differentiable in the overlap region. And we do so by claiming that the two descriptions are related by a dual supertranslation transformation, MF, with a parameter f that is equal to the difference between the two boundary gravitons. And this is given by the following expression, minus 8i log of the absolute value of z. This transformation parameter is regular in the overlap region, and therefore it describes a regular dual supertranslation transformation in the overlap region. And since I provided evidence suggesting that dual supertranslations describe an unobservable redundancy, the two descriptions in the overlap region are physically equivalent. And this is the claim. And finally,
I would have expected this formula to have the argument of C. So log of C over C bar. And so that the time in the North Pole is the time in the time in the northern chart is equal to the time in the southern chart plus the.
So I'm getting to this point, but here note that I do not perform a diffeomorphism. So the time is globally defined, and the coordinates are globally defined. And the global charge of the charge of this monopole is non-zero. It receives equal contributions from the north and south patches, such that the total charge is the same as the NUT charge. And yeah, now I want to compare this with the approach of Meissner, or with the Meissner's interpretation. This can be extended to a nonlinear solution using the metrics that describe two semi-infinite strings pointing in opposite directions. And we can repeat the same exercise as I did for the asymptotic monopole. And this approach that I presented provides an alternative to Meissner's construction. Meissner did precisely what Juan and Ed said. He identified the two patches. So basically the approach was similar, but he didn't know about dual supertranslations. So what he did, he used diffeomorphisms to glue the two patches on the equator. And the change of coordinates, or the diffeomorphism needed for that, is written here. It relates the time coordinate in the north patch and the time coordinate in the south patch in the following way. And here note that they are related by the azimuthal coordinate phi, which is compact, and therefore the time also have to be identified on the circle, and this is that causes the appearance of closed time-like curves, and is regarded as a pathology in the literature. But in our approach, we do not use diffeomorphisms. We instead use the new dual supertranslation transformation, and therefore the time in our construction is not compact. So this is the difference, that we use the new dual supertranslation symmetry as opposed to diffeomorphisms like Meissner. Finally, we are still not guaranteed that there are no closed timeline curves because the coordinate phi is compact and could potentially become time-like. But it turns out, and that can be shown explicitly, that there is a certain region of parameters in which that never occurs. And the region of parameters is given by the following bound on mass to NUT charge ratio. It turns out that when the ratio of mass to NUT charge is smaller or equal, this is a typo, smaller or equal to square root of 5/27, there are no closed timelike curves, and phi never becomes timelike. So this is a prediction for the value of these parameters, and it may remind you of the bound on Kerr-angular momentum. The difference is that in our case, it's an upper bound on the mass, and in the Kerr case, it's a lower bound on the mass. But otherwise, they seem to follow from the same principle, which is basically some form of cosmic censorship. Any questions? Okay, since we have 5 more minutes, and I want to present one more application.
I do have a question.
Yes.
So if you want to claim that the S squared north and the S squared south are physically sensible,
Yes.
we don't have to go to null infinity to discuss that question. Let's just discuss it in the bulk of the spacetime. You've written 2 different metrics, and claiming that in some region they're physically equivalent in general relativity is normally accomplished by making a change of coordinates between the 2. And remember, we're not at null infinity. We're just in the interior of the space-time as you've written it down.
Yes, so I should mention, I should emphasize that everything that I'm doing is only asymptotic.
Well, not so. You've written down a formula for a 4-dimensional metric. In fact, 2 formulas.
Yes, but
the S squared n and the S squared s are 2 4-dimensional metrics. And if you want to claim that they're physically equivalent, you should establish that claim by making a diffeomorphism between them, which is given by that formula of Misner's that you've written down.
No, of course. I do not claim that. I only claim we have only an asymptotic analysis. So it is true, we cannot prove that everywhere in the bulk there are no closed timeline curves or singularities, only asymptotically.
No, on the contrary, you can see that there are. If you do not make this identification, then in the bulk it's clear that there are singularities.
Yes, in the bulk there could be. Our analysis is only asymptotic. In the bulk,
do better than to say there could be. You can see them.
Yes, so everything. So I should, yes, we avoid only asymptotic. We avoid only asymptotic closed timelike curves that approaches null infinity. This is absolutely correct. However, it is possible that this can be extended into the bulk using a nonlinear extension of dual supertranslations, but this is out of the scope of this talk. This is absolutely correct. I emphasize that everything that we are doing is asymptotic, and we don't know if in the bulk there are any other singularities, closed timeline curves, or...
I don't know why you don't know, just looking at your formula.
No, sure. With the knowledge we have now, we can only, in the bulk, we can only use Meissner construction.
In the bulk, you can only claim that those 2 spacetimes are the same if you're willing to make this diffeomorphism to relate them.
Absolutely correct. I do not, yes, I do not.
But when you do that, that means that in the bulk, there are closed timelike curves.
Yes, this is true. Again, I want to just say that it is possible that the dual supertranslation transformation can be extended into the bulk, in which case one can also address this problem in the bulk, but that it's out of the scope of this talk. Absolutely. this is, we are working on extending dual super translations into the bulk, but I hope to report on it soon, but this is still not established and out of the scope of this talk. So yeah, I emphasize we managed to avoid closed time curves only asymptotically. So as an asymptotic observer, will not see a closed time curves in this scenario, but yes, if he goes into the bulk, he will see.
You can extend this metric for large R, and you already see the problem, right? As I was saying. So,
well, I claim is that at null infinity we can use dual super translations instead of diffeomorphisms. So this is the claim.
Well, it seems to give a claim that is contrary to what you explicitly see by taking that previous metric that you had in the previous transparency.
Yes, but yeah, I just want to say that we can take these matrices and glue them only asymptotically. That's the claim, not more than that. Only asymptotically. Yeah, so if you don't like this form of the metric, I mean, I agree. We don't have an argument for the bulk, but asymptotically we can identify them in this way. But we don't know yet how to extend this monopole solution into the bulk. Hopefully, we'll be able to do it, but we don't know how it is extended into the bulk. So I'm running out of time, but let me briefly mention another application, which is an electric magnetic duality. So in the literature, there is a solution generating technique known as complex coordinate transformation, and it provides a set of maps between different solutions. For example, there is a map between Schwarzschild and Kerr matrices that is given by a certain complex coordinate transformation, and there are similar maps to different metrics, and in particular for the Taub-NUT. But the mechanism behind these complex transformations remained obscured, even though they are known in the literature for many years. So recently there has been some progress made in this direction by Nima, Yutin, and Donald, where they suggest or argue that the complex coordinate transformation that maps Schwarzschild to Kerr originates from exponentiation of certain spin operators. What I would like to suggest now is a underlying physical mechanism for the map between Schwarzschild and Taub-NUT. This map takes the following form. It was discovered by Talbot. And we have shown that first of all, this complex coordinate transformation corresponds or equivalent to a super translation transformation with an imaginary transformation parameter given by the following formula. And furthermore, it takes the super translation charge to a complex combination of super translation and dual super translations. Yes, so therefore we interpret this coordinate transformation as a duality operation, for which the global part takes the mass to the complex a complex combination of the mass and the NUT charge. And furthermore, one can define a complex charge in which the duality operation corresponds to shifts in the phase. And this can be extended to a general class of metrics that admit a double copy structure, written here. This class of metrics can be used to construct a gauge field from the metric components that solves the Young-Mills equation. This is something that is well known in the literature and heavily used by many groups. And under the double copy structure, we showed that the gravitational charges, supertranslation and dual supertranslations, are mapped into the electric and magnetic charges. So the double copy structure provides a concrete and direct map between the charges and elevates it to more than just an analogy, at least for this class of metrics. It also means that the duality that we argued between standard and dual supertranslations is related by the double copy structure to electric-magnetic duality. So we have this set of maps between these three solutions. As Nima and Yutin and Donald showed, Schwarzschild is related to Kerr by exponentiation, by an operation that is an exponentiation of spin operators. And then we also have the map from Schwarzschild to Taub-NUT as a duality operation. So that provides a small set of map. And let me conclude with some future directions. One of them is to extend, this is point 5 here, to extend this set of maps to the entire class of solution that is known as the Plebanski-Demiansky family of solution. That includes 7 parameters. And this is regarded as a general class of solutions in general relativity. More directions that we are pursuing or plan to pursue is to try to derive a quantization condition for the monopole. We also try to address the problem of angular momentum in GR using these tools. I think that it will also be interesting to see if the super selection structure that I described can be useful in addressing the black hole information paradox. It will also be interesting to see if what are the observational signatures of such a monopole. And we also, I think that it will be nice to extend this analysis also to spacetimes that are symptotically de Sitter and anti-de Sitter. And finally, I would also like to understand how this is translated to some dual theory in the sense of flat space-time holography. So I will end here.
All right, thanks. Thanks for the talk, Uri. Are there any questions for Uri?
Hi, Uri. I can ask a question.
Yes.
So in the electromagnetic case, I guess one of these boundary conditions that you choose, I can understand them as imposing a boundary condition on some linear combination of F and its hot dual, right?
Yes, exactly.
And that kind of defines where I am putting my degrees of freedom in terms of gauge fields. What is the version of this statements in the gravity case? What plays the role of F and star F?
Okay, yeah. So that's a good question. We can define a gauge field. Let me go. We can define these two potentials. Phi is the analog of the scalar potential in electrodynamics, and A is the analog of the vector potential. Okay. Now, there is a non-trivial result which says that this potential that I defined here using the metric components, okay, so this is something that I defined using the metric components, and it turns out that under dual supertranslations, this vector field A transforms as a U1 gauge field, where the transformation parameter lambda is related to F by this following formula. Okay, this is a non-trivial result because, for example, it is not true for standard supertranslations. Under standard supertranslation, this vector field that I defined doesn't transform like a U1 gauge field. It transforms as diffeomorphisms covariantly. Now, it turns out that the dual supertranslation charge can be written as an integral over the field strength constructed from this gauge field. So it looks exactly like the magnetic field in electrodynamics. And in a similar way, the bonding mass is similar to the scalar potential, but this similarity is only, let's say, cosmetic, because the physical meaning of the charge associated with this degree of freedom is not at all redundancy, but rather physical diffeomorphism. So one can draw the analogy here as well with the electric charge, but this is just an analogy. Does that answer the question?
Yeah, I guess so. I was expecting an answer, maybe, but maybe I'm wrong. I was expecting an answer like, you know, assuming that dF equals 0 in electromagnetism is like assuming zero torsion in general relativity. I was expecting something like that, but maybe this is the wrong intuition.
Yeah, I'm not sure about that. In QD, you can define, let's say, a boundary photon. Okay, this phi is different than the phi that I introduced here, and it also has real and imaginary parts. And the ionic boundary condition will relate the imaginary part of the boundary photon to the real part. So this is the analogy with electrodynamics, and it can also be written in terms of the field strength, I believe.
All right, thanks.
Yeah. Any more questions?
Yeah, I have another question. This is maybe a bit technical. So one of the things that motivated the original boundary condition, that real part of C, imaginary part of C is 0,
yes,
was to insist on finiteness of the symplectic form on the asymptotic symplectic form. So if you follow this the covariant phase space formalism and you construct the phase space for gravity on null infinity, you naively get a divergent symplectic form.
Yes.
And one of the, if you set the real part of C to be 0, then it turns out that all the divergences cancel out and you end up getting a finite symplectic form. So I was wondering, in what sense, so you wrote down the charges, so therefore you have some symplectic form which can show that the commutator of that charge, your M of F, with the gravitational modes actually generates these dual transformations that you're talking about. So I'm wondering how the symplectic, if it's also true that this extension also gives you a finite symplectic form.
Yeah, that's a good question. I'm not, we didn't check the symplectic form. Let me tell you what we did show. So this is Bra, right?
Yeah, yeah.
So Bra, you showed in your paper that the boundary conditions are needed in order to have the correct Dirac bracket between the super translations and the radiative data.
Yes.
And the claim is that this boundary condition is doing the same thing. Yeah, one can show it explicitly, but I only alluded to the physics.
So you derived the Dirac bracket, and it was
we derived the Dirac bracket.
Okay,
yes.
So then the symplectic form is
yes. So yeah, so that was my claim, that this boundary condition is solving the problem that the puzzle that you identified in the same way. I didn't show it explicitly, but I was trying to explain the physics, and the physics is that it relates, it puts a constraint between the two polarization modes of the graviton at 0 energy. Yeah, and this is related. The factor, you found here a factor of 2.
Yes.
And this factor of 2 comes from counting incorrectly the number of degrees of freedom.
Yes.
So this factor of 2, we get this factor of 2 only when we count correctly the number of degrees of freedom. And this is why this boundary condition works.
Uri, can I ask? I still didn't understand the the answer to the question raised by Edward and Juan. So the metric in the bulk clearly has a problem. When you say that that you're thinking about extending the dual translations into the bulk, what do you mean? Do you mean that you're looking for something that's not a diffeomorphism, a different bulk redundancy, which might cure the problem?
Yes, but I don't know that yet. That's what I'm suggesting. This is work in progress, but so far what I present is only the asymptotic analysis.
Okay.
I think that dual super translations can be extended into the bulk, but yeah, this is out of the scope of this, and I still don't know that. So yeah, in the bulk here, the monopole solution can have maybe a pathological behavior, we don't know. But hopefully it can be extended into the bulk, and I hope to report on it sometimes in the near future.
Have you looked at super rotations at all?
Yeah, we are looking at it now, and this is related to the last part of the talk, the problem of angular momentum. Yeah, so we are looking at this now. One thing that I can tell you, and again, this is work in progress, so this is only my point of view on this. It turns out there are works by Chris Pope and Geodesic Equation that show that there is in fact a tower of BMS charges. So at leading order, there is T super translations and dual super translations, and then there are subleading orders. Now, at leading order, T is basically a description of the mass, and M is description of the NUT parameter. So this is like a magnetic monopole. And it turns, and let's put it this way, I suspect that at subleading order, the subleading dual super translation charge describes angular momentum. And the reason that I suspect that is that in the geodesic equation, the angular momentum of Kerr gives a magnetic field of a dipole. So that suggests that Kerr angular momentum is subleading dual charge.
But doesn't the super rotation do that anyway? Isn't super rotation giving you
right? So yes, so hopefully I'll be able to report soon on the connection between super rotations and the subleading dual charges, and that could potentially clarify, or let's be modest, that could potentially be helpful in addressing the problem of angular momentum. This is work in progress, and I have to report on it soon. In particular, it implies that there should be a dual angular momentum.
But you don't expect there to be an infinite tower of such charges, right? Because roughly each tower gives you a soft theorem, and you don't have an infinite tower of soft theorem.
Absolutely correct. So that's also a good question to ask. So they worked in the linearized theory, and as Newman and Penrose already noted, in the linearized theory, there is an infinite tower of charges, but they collapse to finite amount of charges in the nonlinear theory. So that's also a question that is interesting, and that we are thinking about, how these two things are related and how the tower of charges sums up to a finite amount of charges. Yeah, so all of these questions are very interesting and are currently in progress.
So since you mentioned it, I'll just add a comment. As you said, like you can think of these constraints as relating the polarizations, the fact that the soft graviton doesn't have two independent polarizations.
Yes.
But in the subleading soft graviton actually does have two independent polarizations. I wouldn't expect any non-trivial constraint at subleading order.
You mean, yeah, you wouldn't expect more.
I wouldn't expect dual charges. That's what I'm thinking of, because we don't have any constraint at subleading. But there is no constraint. If you look at the subleading soft graviton theorem, there is absolutely no constraint that relates the two polarizations to each other.
And that may be true. Yeah, I don't have a lot to say about it right now. But there are some claims in the literature that there should be a dual angular momentum. Perhaps there is no new boundary condition needed to define it. But yeah, all of this are good questions that are currently under consideration.
Okay, thank you.
I just want to add one last little question about the question that Nima brought back up. So yes. I'm confused about why having these pathologies in this metric is a problem at all. I mean, if we look at the U1 case again with a magnetic monopole and we try to define some globally defined gauge fields, we will also have problems with the Dirac monopole, right? The issue here is that we're looking at a gauge field we shouldn't be looking at. We should be looking at star F equals dA instead, and then we would find the correct answer. So is that the issue here?
Oh, the issue here is more severe because not only, in the construction of Meissner, Meissner tried to avoid string singularity, but the price he had to pay is the appearance of closed timelike curves. In gauge theory, we don't have this problem. We can have closed trajectories in gauge space. That's not a problem. So yeah, the situation is different in this case, but dual supertranslations provide a new property that is closer or more similar to gauge theory. Yeah, but without dual supertranslations, the problem is real. And what I would like to claim is that dual supertranslations only asymptotically provides a better alternative, let's say, only asymptotically.
All right, are there any other questions for Uri? Okay, if not, let's thank him again. Thanks a lot.
Okay, thank you very much.